Hello, everyone. We actually have one more topic in Module 7 before we finish this. This does seem like the never-ending module, but we are covering a lot of really important topics in this module, which will give us a great foundation for continuing to learn all the other stuff that's coming after we finally finish this module in this course. So let's start talking about that. Let's start talking about the activity series. Now, if you recall, in the chemical reactions lab, you have to actually develop an activity series for the three metals that you worked with, I think it was magnesium, zinc, and copper. And to do that, you had to look at the reactivity of the metals with one another and figure out which one was more reactive, which one was moderately reactive, and which one was least reactive. And that ordering of the reactivity is actually an activity series. What we do here is we look at basically single replacement or single displacement reactions. If I have some element A reacting with some element, so this is usually some solid element, and this is reacting with some ionic solution. And what I end up with is A and B changing places, which means I get AC, a new ionic compound forming, plus a metal usually forming, at least in the ones that we did in the lab, which is a single replacement reaction or a single displacement reaction. Now, it's also a redox reaction because if this is an element, it has an oxidation state of 0. And here, it's going to be an ion. So to form an ion, the metal will lose electrons. So A is going to lose electrons and be oxidized. And then B is an ion, and then now it's a metal which has a 0 oxidation state. So B is going to gain electrons and become reduced. A lot of times we'll see these reactions where the counter ion C, whatever anion that is actually not shown because it really doesn't participate in the reaction. And we really want to look at this oxidation process between the element and the ion. So here I have iron solid reacting with copper 2+ ion. So if I look at this test tube, I have my nail, iron is this nail that's in there, and I have a dark blue copper 2+ solution. The copper 2+ ion is actually a beautifully cobalt blue kind of color, or a darker blue, maybe tealish blue kind of color. And when it's there, you're going to see this beautiful blue color. So during the course of this reaction, my iron is going to get oxidized. It's going to lose electrons, and my copper is going to get reduced. It's going to gain electrons. And what I'm going to see is I have sort of a copper plating that's forming on the ion. And I also know that my blue copper 2+ color is decreasing. So these are observations that you would make if you were doing this in the lab. So this reaction, this iron nail actually becomes sort of coated with metallic copper. It's sort of plating out. And then this intensity of the blue is diminishing as my copper 2 ions are forming that solid copper, and those ions are no longer in solution, providing that beautiful color. Now, the activity series is looking at all types of metals and actually hydrogen, and figuring out what the order of reactivity is amongst these elements in these single replacement reactions. So elements that are higher up are more likely to be oxidized. They're more reactive under these conditions. So the way you read this chart is that any element higher in the activity series will reduce the ion of any element lower in the activity series. So when I look at this reaction here, I'm looking for iron and copper. Iron is here, and copper is down at the lower part of the chart. So iron is more reactive than copper. Iron is higher on the activity series. So iron will displace the copper. This reaction will occur as we see experimentally if we actually did this in the lab. So you can use this activity series to predict the products for single replacement reactions. And what I want to do is always compare the two elements that are in my reaction to see if the element that needs to displace the other element is reactive enough to do that. So let's look at copper and silver. Will copper metal react with silver ion? Remember, this copper then is losing electrons and is oxidized. And this silver, right, this is metallic copper. This is an ion. This is going to be metallic silver, and this is an ion. So the silver ion is going to gain electrons or be reduced. Copper is that reducing agent. Is copper reactive enough to displace the silver, or does the silver displace the copper? Which one of these two reactions actually will occur? So what I want to do is go back up here, and I want to look at copper again, because that's what we're comparing it. But now I'm comparing it with silver. No, copper is more reactive than silver. So the copper is going to displace the silver. The silver cannot displace the copper because the silver has a lower reactivity. So if I look at this, the reaction that's actually going to occur is this top reaction, because the copper is higher on that activity series. And I actually can see this in solution. Here, my copper wire is present, and there is no blue color, which would indicate copper 2+ yet. As this reacts, the copper is going to reduce the silver ions. So this copper wire becomes coated with silver. You're going to see this silver metal is going to be plating out on the copper wire. You're also going to see an increasing blue copper 2+ color as copper 2+ ions, which are blue, which give us that blue color, are going to be produced. So this shows us that this reaction actually occurs. And if I didn't do the experiment, I would predict that this reaction occurs because copper is higher on the activity series and will react with the silver. Again, I don't really care about the counter ions here because they really are spectator ions and they don't do anything in the actual reaction. We can use these types of reactions in order to do titrations as well. We've done acid-base titrations in the past. Now we're going to talk about redox titrations. Just like with acid-base titrations, I need to know the balanced chemical equation for the reaction. We don't learn how to balance these redox reactions in Chem 1 in this class. That is something that you learn in electrochemistry in Chem 2. So if you're taking Chem 2, you'll learn that in the next semester. But what I'm going to notice is I have oxalic acid and I have permanganate ion. Balancing this is actually pretty tough. You have to go through this entire process because you not only have to balance the elements, but you also have to balance the electrons. So there is an entire process that needs to be followed in order to balance these these reactions. It's the balanced equation in this titration, or that is used in this titration. So for this purpose, right, if I give you a redox titration problem, I will also give you the balanced equation for the redox reaction. Again, notice the counter ion is not provided. I know it has a negative charge. Usually this is going to be because I have potassium permanganate, which is going to be the reactive compound. So like the potassium really doesn't matter, but what I'm going to do is I'm going to, it just provides this permanganate ion in solution. So basically, one potassium permanganate compound gives me one potassium plus and one permanganate ion. So I can use this information in order to determine, if I need to, how much permanganate ion I get if I'm given the amount of potassium permanganate that I have. I'll show you that in the example. Notice here I have a clear solution, and this is going to be the oxalic acid. I have a known amount that is weighed and dissolved. If I have a known amount and I know the molecular formula, I'm going to know the moles of oxalic acid in that solution. Now, up here, I have this purple potassium permanganate solution, which is the permanganate in solution. So this is potassium permanganate. Again, I don't need the potassium in that balanced chemical equation. I don't know the concentration of the potassium permanganate solution. This is what I want to try to figure out. And I'm adding this with the burette. Now here I have this purple color that is going to be persisting. And notice the potassium permanganate is purple, right? So when this purple color persists, this is telling me that all of the oxalic acid has reacted. There is no more oxalic acid to react. So any potassium permanganate, any permanganate ion that I actually add into here is now going to stay unreacted, which is why I get this buildup of purple color, because the color of the potassium permanganate is purple. So I can use this purple color, this light purple color that is persisting here as an endpoint to this type of reaction, and then I can use stoichiometry to figure out the concentration of my unknown potassium permanganate. So let's do an example. Let's say I have a solution and it's got 0.2585 grams of oxalic acid. And I know that I have 22.35 mils of my potassium permanganate solution. This was actually delivered from the burette to get that purple endpoint. So I want to know, in using this titration, I want to be able to calculate what the concentration molarity is of that potassium permanganate solution. So I'm going to use my balanced chemical redox reaction from the mass of oxalic acid. If I know the molar mass of H2C2O4, I can calculate the moles of oxalic acid. So this is just going to be the gram to mole conversion using the molar mass. Now, this conversion from moles of oxalic acid is using the coefficients from my balanced chemical equation. So based on the moles of oxalic acid, I can figure out the moles of potassium permanganate that reacted. Now, if I know the moles and I know the volume of the potassium permanganate solution, I can calculate the molarity of the potassium permanganate, and that gives me the concentration of that potassium permanganate solution. So let's put in the numbers. If I use 0.2585 grams of oxalic acid, this is the molar mass here of H2C2O4. So when I do that calculation, I get 2.871 times 10 to the minus 3 moles of oxalic acid. Now, notice my ratio here is 5 moles of oxalic acid react with 2 moles of permanganate, and this is the mole ratio that I get from that balanced chemical equation. Oxalic acid is going to be on the bottom because I want to cancel. And when I do this, I know that I have 1.148 times 10 to the minus 3 moles of potassium permanganate that was contained in that 22.35 milliliters. That 22.35 milliliters had this many moles of potassium permanganate in it, and I know that because that's when I reached my endpoint. All the oxalic acid was basically reacted. I got that purple color that persisted, and I can calculate the moles of permanganate that it took to do that. So then the next thing is I'm going to convert my milliliters to liters. So this just converts the milliliters to liters. And remember, molarity equals moles over volume in liters. So if I take the moles and I divide by the volume in liters, this is going to be the concentration of that unknown potassium permanganate. So this is how I do a redox titration. You might see one or two in the homework, and if not, you might see one or two on a quiz or a test, so make sure you understand this process. If you do want extra practice, look up redox titrations or ask me for examples that I could give you for this particular process. And finally, that actually ends this crazy module 7. So we are done with module 7, and now we are going to go on to module 8, which is gases and gas laws, and that will correlate to chapter 5 in the Tro book. In the McMurray book, it tracks to chapter 10, I believe. But whatever chapter it is in your particular book, it is going to cover gases and gas laws. Have a good night.